Deep beneath the ocean, silence is not what it seems. It is only a signal we have not yet fully understood. Welcome to Relaxing Facts Studio, where we explore the hidden systems shaping our planet through sound, pressure, and light, revealing what exists far beyond the surface of everyday perception. And today, we descend into the ocean's most extreme environments, where pressure reshapes physics, sound becomes distorted, and life adapts in ways science is still working to fully explain. Stay with us as we uncover what the deep ocean is really doing beneath the noise right now, below everything we know. Long black lines stretch silently across the ocean floor, carrying nearly all global internet traffic through submarine cables. They follow stable regions of the seafloor to reduce rupture risk from tectonic activity. These routes are not random. They trace geological calm zones. Major landing stations act as concentrated data gateways, where entire continents connect through a few physical points, creating measurable infrastructure bottlenecks in the global network. That physical presence alters the seafloor more than expected, especially during installation and long-term operation. Heavy cable-laying equipment disturbs sediment layers, reshaping microterrain along the route. The change is subtle but persistent. Signal repeaters placed every 50 to 100 kilometers generate continuous low-frequency vibrations, introducing localized acoustic anomalies detectable by hydrophones near cable corridors. Those localized effects expand across a massive system spanning over 1.4 million kilometers of active submarine cables worldwide. This network forms the physical backbone of the Internet. It is larger than it appears. The density of cables increases near coastlines, where multiple lines converge, amplifying both mechanical disturbance and electromagnetic overlap in confined underwater regions. That concentration creates unintended interaction zones where marine navigation systems begin to shift behavior. Some whale migration routes show measurable deviations near dense cable regions. The pattern is not uniform. Electromagnetic fields and low-frequency vibrations overlap with biological sensing ranges, potentially forming low-activity marine corridors where species reduce movement without complete avoidance. Unlike natural ocean features, this system is not passive. It is strategically monitored and increasingly defended. Submarine cables now represent critical infrastructure, vulnerable to disruption and targeted interference. Control means leverage. Nations actively track and secure these routes, transforming the ocean floor into monitored digital territory where physical geography and information flow are tightly linked. Warm and cold water layers stack across the ocean, bending sound in ways that create invisible gaps known as acoustic shadows. These zones block or redirect sound waves, making objects temporarily undetectable. They form naturally. At thermocline boundaries, sound refraction shifts direction due to temperature gradients, creating zones where even advanced sonar systems lose signal clarity and spatial accuracy. That loss of sound clarity does not affect sharks in the same way, because they do not rely on hearing alone to detect prey. Instead, they sense pressure changes directly. The difference is fundamental. Using a system called the lateral line, Sharks detect micro-vibrations in water movement, allowing real-time spatial awareness without relying on reflected sound waves. That sensory advantage operates across wide vertical hunting zones, especially in layered water where acoustic shadows are most stable. Sharks position themselves below prey movement paths. The geometry is precise. By aligning with these blind zones, they remain undetected while tracking motion through pressure gradients that extend several meters beyond the prey's physical position. That positioning allows sharks to time attacks through moments when prey enters acoustic gaps, reducing detection probability to near zero. Energy use stays minimal. This strategy optimizes predation efficiency, using environmental physics instead of speed or force, especially in low visibility conditions where other predators rely on sight or sound. While human sonar systems struggle in layered thermal structures, sharks operate unaffected within the same environment. Engineering attempts to replicate this detection method remain limited. Biology still leads. Evolution has produced a sensing system that adapts instantly to environmental distortion, something current technology cannot fully reproduce in dynamic underwater conditions. Superheated water bursts from cracks in the ocean floor, producing a constant hissing sound as it mixes with near-freezing seawater. The contrast is extreme. Temperature differences can exceed 700 degrees Fahrenheit. This rapid exchange creates turbulent flow zones, where chemical reactions and pressure release generate continuous acoustic signatures known as hydrothermal vent emissions. That sound comes from more than just escaping fluid, as the surrounding rock is also under stress from tectonic movement. Plates shift slowly beneath these systems. Friction builds continuously. As rock layers grind and adjust, they produce low-frequency seismic vibrations, adding a deep mechanical layer to the acoustic environment around active vent fields. Those combined sound sources extend across entire mid-ocean ridge systems, forming one of the largest continuous geological networks on Earth. The scale is massive. Over 40,000 miles of ridgelines exist globally. Clusters of vents act like distributed energy points, each contributing localized sound that merges into a wide background of geothermal and tectonic activity. That continuous output turns hydrothermal regions into persistent energy systems where heat transfer directly influences acoustic behavior. The process never fully stops. Energy flows upward constantly. Variations in vent activity can change local sound intensity, linking geothermal cycles to measurable shifts in underwater vibration fields. Unlike surface ocean noise driven by weather and waves, these sounds originate deep within the Earth itself. They do not depend on external conditions. They come from below. This makes hydrothermal vents a stable, long-term acoustic source, operating independently from atmospheric influence and revealing internal planetary processes through sound. Small flashes of blue and green light appear in complete darkness, triggered by living organisms deep below the surface. There is no heat. The light is chemically produced. Through a reaction known as bioluminescence, specialized molecules release photons efficiently, often inside dedicated organs called photophores distributed across the body. That light is not random. as many species control its timing and intensity with precision to send information. The flashes follow patterns. They act like signals. Organisms use structured sequences for mating, warning, or hunting, forming species-specific communication systems where timing functions as encoded biological language. Those signals extend beyond individuals, especially in colonial organisms that coordinate behavior across multiple body segments. The system becomes collective. It operates as a single unit. In siphonophores, thousands of connected bodies synchronize light pulses, creating distributed control systems without a central brain, yet maintaining coordinated responses across the entire organism. That coordination suggests complex information processing emerging from simple biological units, without relying on centralized control. The behavior appears organized, but limits remain. Science can observe synchronization patterns, yet the exact decision-making mechanisms behind these light-based systems are not fully understood at the neural or biochemical level. Unlike surface communication that depends on sound or physical movement, this system relies entirely on light in an environment where visibility is otherwise near zero. The difference is fundamental. Light replaces sound. In deep water, optical signaling becomes more reliable than acoustic methods at short range, especially where pressure and density distort traditional sound-based communication. Sound still travels at the deepest point in the ocean, even under crushing pressure inside the Mariana Trench. The environment is not silent. Pressure exceeds 16,000 psi. At these depths, water density alters how waves move, compressing frequencies and distorting signals as they pass through what scientists define as the Hadal zone. That distortion changes how sound behaves, especially as higher frequencies lose energy faster than lower ones. The shift is measurable. Signals become stretched and muted. Under extreme pressure, wave propagation favors low-frequency transmission, while high-frequency components degrade, reducing clarity and altering how acoustic information is received. Those effects extend across a trench system nearly 1,580 miles long, forming one of the most extreme acoustic environments on Earth. The scale is difficult to visualize. It is deeper than Mount Everest is tall. Within this space, multiple sound sources combine, including tectonic activity, vent emissions, and distant ocean noise traveling across vast underwater distances. That layered sound environment includes signals that scientists cannot fully classify, despite advanced recording tools like deep-sea hydrophones. The data remains incomplete. Patterns appear without clear sources. Some recorded rhythms suggest biological origin, but current models cannot confirm whether they represent communication systems or unknown environmental processes. Unlike isolated natural systems, this deep environment now includes human-generated noise reaching even these extreme depths. The boundary is no longer sealed. Sound travels farther than expected. Shipping activity, sonar pulses, and industrial exploration introduce artificial frequencies, creating a hybrid soundscape where natural and human signals overlap in the deepest ocean layers. Fossilized shells often preserve spiral shapes that look perfectly engineered, even after millions of years underground. The geometry remains stable. Ammonites are a key example. Their curved chambers form repeating cavities that can still reflect and trap sound waves, even when the original biological material has been replaced by minerals. That structure behaves like a natural resonance system, where internal spacing influences how vibrations move through it. The effect is physical, not symbolic. Air pockets once existed. In modern acoustic modeling, these shell geometries are treated as resonant chambers, where wave reflection depends on cavity size, wall density, and spiral curvature. Those resonant properties can be simulated across large fossil datasets, allowing researchers to reconstruct how ancient ocean environments may have sounded. The scope is broad. Entire ecosystems can be modeled. By comparing thousands of fossil structures, scientists estimate that prehistoric seas likely had higher baseline acoustic energy due to denser marine life and more frequent large-scale biological movement. That reconstruction suggests sound may have played a stronger role in ancient marine ecosystems than previously assumed, influencing movement and interaction patterns. The evidence is indirect, but still measurable. Because sound itself does not fossilize, researchers rely on physical proxies like shell density and structure, which limits certainty in sonic paleontology interpretations. Unlike modern oceans filled with industrial noise and navigation signals, ancient seas had no human-generated acoustic interference. The baseline environment was purely natural. No artificial frequency existed. This makes fossil-based acoustic reconstruction a comparison between a silent geological archive and a now fully active, noise-filled modern ocean system. Thin fiber optic lines run across the ocean floor, silently carrying most of the world's internet traffic. They are physically small but globally essential. Over 95% of data travels this way. These submarine cables connect continents through landing stations that act as high-concentration data entry points into national networks. That constant data flow depends on signal repeaters placed along the cables, which boost optical signals at regular intervals. The system is highly engineered. Repeaters sit every approximately 60 to 100 kilometers. These devices introduce slight electromagnetic activity and micro-vibrations that can be detected in sensitive deep-sea monitoring systems. Those cables form a network stretching over 1.4 million kilometers globally, making it one of the largest human-made structures on Earth. The scale is immense. It crosses every major ocean basin. In dense regions near coastlines, multiple cable paths converge, creating concentrated infrastructure zones with overlapping physical and electromagnetic effects. That concentration can subtly influence marine behavior, especially for species that rely on electromagnetic or vibration-based navigation systems. The effect is not fully mapped. Behavioral shifts are observed. Some marine mammals show altered movement patterns near high-density cable corridors, suggesting sensitivity to low-frequency environmental changes. Unlike natural seabed features, this network is continuously monitored and strategically protected due to its importance to global communication. It is not passive terrain. It is critical infrastructure. This turns parts of the ocean floor into a managed digital layer, where physical geography directly supports global information exchange. Even in deep ocean regions, marine mammals continue showing regular rest cycles while background noise never fully disappears. The environment stays acoustically active. Low-frequency sound dominates. Because water carries vibrations efficiently at roughly 1,500 meters per second, distant sources like storms and ships remain detectable far from their origin. That constant exposure does not prevent rest, but it changes how species like whales and dolphins sleep, using a split brain system. The mechanism is specialized. It is called unihemispheric slow-wave sleep. One hemisphere of the brain stays active for breathing and awareness, while the other enters a recovery state, allowing continuous surface control without full unconsciousness. Those rest patterns operate across entire ocean basins where shipping lanes form continuous corridors of mechanical noise. The scale is global. Thousands of vessels operate daily. Propeller cavitation and engine vibration generate persistent low-frequency signals, often between 10 and 200 Hz, which travel long distances with minimal energy loss underwater. That persistent noise layer can interfere with communication and rest cycles, forcing marine mammals to adjust movement and behavior over long periods. The effect accumulates slowly. Energy budgets shift over time. Extended acoustic exposure has been associated with increased disorientation and altered migration timing in some populations, though responses vary by species and region. Unlike natural ocean soundscapes shaped by wind, waves, and geological activity, modern deep-sea environments now include continuous industrial vibration. The baseline has changed. Silence no longer exists. This overlap creates a hybrid acoustic system where biological rhythms must adapt to a constant human-generated noise floor embedded within the ocean itself. As depth increases, the ocean becomes noticeably quieter, even though energy is still moving through the water. The change is gradual. Pressure rises roughly 1 atmosphere every 10 meters. This compression alters how water molecules vibrate, reducing the efficiency of sound wave formation compared to surface conditions. That reduction happens because sound depends on particle motion, and extreme pressure restricts how freely those particles can oscillate. The effect is physical, not abstract. Molecular spacing becomes tighter. In denser environments, acoustic waves lose high-frequency components faster, a process driven by increased damping and energy dissipation within the fluid medium. Those changes accumulate across the entire water column, from surface turbulence down to Hadal depths exceeding 10,000 meters. The gradient is continuous. Each layer behaves differently. Surface zones carry chaotic wave noise, while deeper regions filter out higher frequencies, leaving only long wavelength vibrations that travel farther but carry less detail. That filtering effect reshapes how life adapts to extreme depths, where organisms rely less on sound and more on pressure and vibration sensing. The biology shifts. Different senses dominate. Evolution favors non-auditory detection systems because traditional hearing becomes less reliable as acoustic resolution breaks down under sustained compression. Unlike the assumption of total silence, the deep ocean is not empty of sound. it is structurally limited sound, shaped by physics rather than absence. The difference is critical. Sound is still present. It is simply constrained by pressure-driven physics that determine which frequencies survive, and which disappear long before reaching the deepest layers. What you've just experienced is a reminder that the ocean is never truly silent. Every layer carries motion, pressure, and hidden systems still being uncovered beneath extreme depths. If you've made it this far, thank you for staying with us on this journey. This is Relaxing Facts Studio, and if you haven't subscribed yet, now is the perfect time to join. Share this episode on your social media to help others experience it as well. Leave a like to help the video reach a wider audience and support the channel. Most importantly, leave a comment sharing your thoughts and support.